Hello, gentlemen, and welcome to today's lesson on Hess's law. You'll find this note in the thermochemistry unit under Hess's law. Feel free, or you should, take notes as you watch this video. Feel free to pause or rewind as we go along. So the first thing to understand and to review here is that enthalpy is a state function. And what that means is it's really about the state that it's in at the time. So from the beginning to the end, we don't really care how we get there. So it doesn't really depend on the pathway it was taken. It's going to get there, it's going to get to the same spot, and that's all that we care about. So to help visualize that, think of a staircase. Okay, if we have 3 steps, and our goal is to get from here, part 1, to the top here at C, it doesn't matter whether we take the steps to get here or whether we take a straight line, right? The direct path from A to C is equal to the sum of A to B and B to C. So again, even though a direct line may look more advantageous, it really doesn't matter. We're still going to use the same amount of energy either way as far as enthalpy goes. So this concept, this idea is known as Hess's law. So in going from a particular set of reactants, so Hess's law states that in going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So if you look at our example here, the oxidation of nitrogen, producing nitrogen dioxide, it can be carried out in one step where the enthalpy change is represented here by delta H1. So you have an enthalpy change here of 68 kilojoules. But it can also be carried out in 2 distinct steps where you have an intermediate. So it's produced in one step, then consumed later in another. So when you can see in this step, the reaction of nitrogen gas and oxygen gas produces nitrogen monoxide. Nitrogen monoxide then reacts with oxygen gas to produce the nitrogen dioxide that we saw in the first equation. And you'll notice that if you cancel out the intermediates, because it's produced and then consumed later, the final reaction is actually the same as the overall reaction in one step. And so what we can do is we can use the enthalpies of each of these individual reactions, add them up, and we will get the same enthalpy as if we went from we did it in one step. Right, so the net reaction is determined by adding the 2 steps together and removing the compounds that are found from both sides of the equation. The enthalpies that also add together give the enthalpy for the overall reaction. Right, so that's just me restating what we've just done. A couple things to keep in mind when you're determining enthalpy using Hess's law. The first is that if a reaction is reversed, the sign of delta H is also reversed. So generally what you're going to see in questions like this is you'll see the overall reaction that we're trying to understand and we're trying to get the enthalpy for, and you'll get a series of reactions and intermediate reactions that build up to that overall reaction. And in some cases, they're in the opposite direction of what we want. So if you were to reverse the direction of a reaction, you would also reverse the sign of delta H. You also may need to change the magnitude of the ratios within that product. And if that were to happen, you also have to change the magnitude of delta H. So it's important to understand the proportion of delta H, or delta H is proportional to the amount of reactant and product in the reaction. If the equation is multiplied by an integer, and if you do multiply it by an integer, you have to multiply everything in that reaction by that integer. And the same goes for the delta H. So my suggestion here, and some hints, is to work backward from the final reaction. Use the reactants and products in that reaction to help you manipulate the other reactions that you're given. So you need to see which side of the reactants your products and reactants are on, and if you need to flip any reactions. Leads me to number 2, you should reverse any reactions that you need to get them in the right order. Again, you may need to multiply reactions by either fraction or whole numbers to give you the required number of reactants, and cancel reactants and products that are on opposite sides. And those will end up being those intermediates that are produced but then later used up. Okay, you should note that reactants and products that are canceled have to be in the same physical state to work out. Okay, so let's look at a couple examples to help us out with this. The first is here in this carbon to graphite, graphite to diamond example. There are two forms of carbon, graphite, which is the soft black slippery material used in lead pencils and as a lubricant for locks, and diamond, the brilliant hard gemstone. Using the following enthalpies of combustion for graphite and diamond, calculate the delta H of conversion of graphite to diamond. So the first thing we need to do, we need to look at our final reaction, right? It's what we're trying to get the delta H of this. Okay, we need to see what side of the reaction each thing is on. We notice that graphite here is on the left, is the reactant, and diamond is our product. We're starting with graphite, and we see here graphite is part of reaction 1. So I'm going to write reaction 1 down with my graphite in the solid state. It reacts with oxygen gas to produce carbon dioxide gas. Now, next thing to notice is we also have a reaction here, an intermediate reaction with diamond available. However, it's on the reactant side. So we're going to rewrite reaction 2 below that, but we're going to reverse the order. So we'll write CO2 gas breaks down to produce diamond and oxygen gas. Now we're also going to write the enthalpies beside them, which we saw above. We're going to rewrite those down. And this is the important part. Because you reversed reaction 2, you need to reverse the sign of its enthalpy. Okay. Now you're going to look on both sides of the equation. You're looking for things that occur on both sides in the same state. So for example, oxygen gas, I have 1 mole of oxygen gas on the left, 1 mole on the right, so those cancel. Same with the carbon dioxide. So my total reaction, as I add it up, I get C graphite in solid state producing diamond in the solid state. So this is my final reaction. Everything works out, everything else cancels out. I'm left with my reaction that I'm looking for. And if that's the case, you can now just add your enthalpies together. So I take my negative 394, add 396, and my final delta H for the formation of diamond is 2 kilojoules. Okay, let's try another example, a little more complex, with a few more examples. So this is now deals with diborane. It's a highly reactive boron hydride that was once considered as a possible fuel for the US space program. We're going to ask you to calculate delta H for the synthesis of diborane from its elements according to the following equation. So again, this is our finished product. This is what we're hoping to get to by the end. So we have our 4 reactions that help us get there. Let's start with reaction 1. We see boron, solid, the element on the left of our reaction, and we see it here in reaction 1. So that tells me that it's on the right side and it's in the right ratios. So I'm going to keep this reaction in the same form that it's in. And I'm going to write my enthalpy for that one. Okay, reaction 2. Now, reaction 2, I notice that I have my diborane on the reactant side. And I can also see the diborane is on my product side in my overall reaction. I don't see diborane in any other reactions, so I'm going to flip this reaction around. So I'm going to move my products to the reactant side. My reactants to the product side. But if I do that, again, I have to adjust my, and to do that, I change the sign from negative to positive. Now I move on to reaction 3. Here I'm looking for my final reactant, my hydrogen gas. I see that in my final formula here, there are 3 hydrogen gas molecules, and I only have 1 in reaction 3. So to deal with that now, I multiply the entire reaction by 3, including the enthalpy. So the entire reaction gets multiplied by 3. So I have 3 hydrogen gas. I have 3/2 oxygen gas. And I have 3 water molecules produced. In doing that, again, my enthalpy is also multiplied, and that leaves me with 858 kilojoules. And now reaction 4. What is the purpose of reaction 4? I have all my reactants and products here. Well, the important thing to understand here now is that I still have some intermediates that I can't cancel. So if I look at both sides of my equation, I have oxygen gas, 2 sets of 3/2 oxygen gas on the left-hand side, and 1/3 on the other side. So those two equal to 3 oxygen gas. However, on the left-hand side, I have 3 water molecules in the gaseous form, and I have 3 water molecules in liquid form. Again, they need to be in the same state, and they need to cancel out. So looking here, I have water going from the liquid state to the gaseous state, which is perfect because you can see in reaction 2, I have 3 water molecules in the gaseous state. I want 3 on 3 gaseous water molecules on the right-hand side, and vice versa. So I do again need to multiply this entire equation by 3, which gives me 3 H2O liquid plus 3 H2O gas. Sorry, produces 3 H2O gas, and my enthalpy of this is now 3 times 44, which gives 132 kilojoules. Okay, and so now I see my gaseous water molecules cancel, as do my liquid water molecules, leaving me with what I need in my equation. Oh, sorry, I also missed the borane. My apologies. Right? So now you're looking through, you're going to pick out the reactants, the products, they match up. I'll add them all up. I get 2 boron plus my 2 hydrogen gas produces my diborane. And now it's just a matter of adding up my enthalpies. So I'm going to add all these up. Sorry, I'm just noticing that in multiplying by 3, I also drop the negatives. So that's a mistake on my part. You should not drop the negatives when you do your multiplication. So if I add up all of these, taking into account the negatives, I end up with 36 kilojoules. So what I'd like you to do now, just to finish up before coming to class, in the homework section, I'd like you to try question 4A. Okay, that'll be the last question here in your Ed puzzle, and you can just type in the answer to finish the question and the Ed puzzle. Thank you. See you in class.